Hello again. This is lecture 2 in a series of lectures on density management. So last time in lecture 1 we went through an overview of the module and the ground that we're going to be covering, and then specifically we dealt with the model of stand development. So we had stages A through E, and for each one of those we had some key points that were associated with each of those stages, and those are important. And if you've forgotten those, you need to go back and review them briefly. But the broadly, we dealt with the nature of competitive interaction at various stages, and that includes both the individual tree, is it growing at its potential or less than the potential, and so on. But then the counter to that is what's happening to stand growth at the or growth at the stand level. And for example, is the population fully occupying the site? Is the stand growing at its potential or at something less than that? And that's associated with competitive interaction. Now, something that is as we talk about stand dynamics, about stand development, there is up to, not necessarily including stage E, but up through stage D, there's an increase in average size coupled with decreasing numbers once self-thinning starts, and so we're gonna deal with that. And we'll, as we move along here, we're going to talk about the interaction of growth rates with the initial density. And we reviewed the idea of a leaf area plateau for the population. This was this is an emergent property. So for an individual tree, leaf area, the amount of foliage that an individual tree is carrying, in principle, continues to increase throughout its life. The rate of increase slows down as the tree ages, but in principle it continues to increase forever. That could be a 300-year-old tree. Now the exceptions, there are always exceptions to that. The tree could have the top blown out of it by lightning or something of that sort, but that's the idea. In contrast, for the population, there is this carrying capacity. There's a plateau, and we'll spend some more time talking about that. But that's a surrogate. That's an indicator. It's a construct that is that we can use to think about what we're doing with redistributing growth and that sort of thing. Okay, so we're gonna, in this lecture, we're gonna address size-density relations. So this is the density being, for example, trees per acre. Size, we can quantify that in different ways, but this is typically a mean size, so like quadratic mean diameter, some people use mean volume, and so on. So the size density relations are a way to quantify relative density, which is very important to us. We have to have a way to quantify relative density. And this is a way to characterize desired future condition. We might say, for example, that in the future we do not want our stand to enter stage D. We don't want any self-thinning, for example. We have to be able to quantify. We have to be able to quantify that to develop silvicultural alternatives. And fundamentally, this is the relative density is a basis, and the size density relationships on which relative density is based is the basis for designing density management plans. Relative density is important. Now these two cartoons are kind of cute, I think. Increasing stand density on the x-axis for both of these figures. That truth be told, that should be relative density, and it's axiomatic among silviculturists that bad things are more likely to happen at high relative densities than at low relative densities. Again, we could find exceptions to any generality, but it's really true. The change in fire behavior from a surface fire to a crown fire, for example, is supposed to be implied by that figure, the upper figure. At high relative densities, your stand, the individual trees that make up the stand, are more at risk to any number of environmental challenges associated with insects and diseases. With regard to insects, that's pretty much true. Whether we're talking about bark beetles or defoliators, bad things happen to good trees at high relative densities. Okay, size-density relationship. This is the predictable, and the emphasis here is predictable, relationship between mean size and density in crowded populations. Now, for the time being, we're going to restrict ourselves to stage D, or perhaps the latter portion of stage C, so a stand that's either self-thinning or is about to. So that's what we'll just use the code crowded here. So we're really talking about stage D sorts of populations. Now, this predictable relationship, which we're going to explore here in a moment, is in fact another emergent property. So the first emergent property that we talked about was that plateau of leaf area in a population of trees. Well, this the predictable size density relationship is another emergent property. So if we were to look at the size, the increase in size of an individual tree, with or without competition, for our purposes right now that doesn't matter, but the size is going to increase pretty much over the life of the tree. Now, again, depending on how you're quantifying size, if it was mean volume and you lose the top of the tree, that might actually go down at some point. But the principle is solid here, that you've got this increase in size indefinitely for an individual tree. Now, the density, and this is absolute density, and I'll remind you that we use density in two ways. Absolute density refers to, that's count, so that would be trees per acre, trees per hectare, so on. Relative density we'll get to in a moment, but for now we're talking about absolute density. And the idea here is that we have a population of trees, and there is an initial density, and barring accidental mortality, that initial density is maintained up until stage D and the onset of self-thinning. And then there is a progressive decline over time in absolute density. Now, if we had really good data, what you would actually see is sort of a stair step down. You might go a few years with no mortality, and then you get a bunch of it, and then go a few more years without any, and then a bunch of it, and so on. And this represents a hypothetical smooth curve through that. So no relationship between absolute density and age until self-thinning starts, and then you get that negative exponential. Now we're going to look at the relationship. So we have mean size with age, absolute density with age. We're going to take age out of it here, and we're going to look at the relationship between mean size and density, independent of age. And what you see is this. So this is a classic relationship. You've all heard of the negative exponential, the negative 3/2 self-thinning law and so on. This is an example or an illustration of that. There is no time here. So it's just the relationship between mean size and density. Now, we're going to do just a little bit of pre-algebra here to set things up. Mean size here is a function of density, obviously, and in this equation, this negative exponential, the exponent here b really is the slope of this line. So it's the shape. It's a shape function. The larger the absolute value of this coefficient is, the steeper. If this was a -1, that'd be a straight line. Okay. The a coefficient here is simply the level of this line. We could have a whole series of curves, all with the same shape, all with the same coefficient, exponent, just differing in the level. Okay, so they'd have different values of a, all of them parallel. Now, sometimes we'd like to have that relationship, that basic relationship between mean size and density, we want to linearize it. So the relationship is curvilinear. It's nonlinear. That's just the way it is. That's the basic biology, the basic ecology of that relationship. But sometimes it serves our purposes to pretend that it's a linear relationship, and we can do that with a logarithmic transformation. So we could plot the same data with the logarithm of absolute density and the logarithm of mean density, and we get a straight line. And of course, the equation for a straight line, you see the transformation here. We've got the logarithm of density, and here the exponent, what had been the exponent before, we've dropped it down here, and we're multiplying that value times the logarithm of density. And then here's that what's now the intercept, the level. If we have the logarithm of it, we've got an intercept value here. So these are exactly the same. I mean, they represent the same function, ecological function, the same relationship. So the transformation here between one and the other is simply an algebraic parlor trick. Okay, and it just, sometimes it serves our purposes. It's more convenient to look at it as an untransformed relationship. Sometimes we like to look at the log-log transformation, and that'll become clearer as we look at this. So let's look at some data. These are, each one of these points represents data from a ponderosa pine stand, and the data were, I mean, I don't know how many hundreds of them there are there, but many hundreds of of stands that are represented in this figure. And we have the here on the x-axis we have the logarithm of quadratic mean diameter, and on the y-axis we have the logarithm of trees per acre. So for example, this particular stand has a quadratic mean diameter of about 10 inches, and there aren't very many of them. There are only 20 or so of them in that stand. In contrast, here you've got a stand that there are nearly 4,000 of them, but they're pretty small on average. They're 2.5 inches or something like that in diameter. Now, a couple of things that are illustrative here are worth pointing out. There are all these data, and in fact, the reality is that the data, we could go back out in the field and find stands and fill in this figure with stands from that have combinations of mean size and density that are down in this area. There are a few of them down here, but we could have found more. It's just that when the data were collected, they didn't have a lot of interest in collecting. They really wanted more dense stands, more stands that were more fully occupying the site. So that's why we've got this swarm of data here. The other thing about this figure is that there's nothing up here, nothing. And in fact, I could send you out in the field with the mission of coming back with data from a stand that had a quadratic mean diameter of 20 inches and 1,000 such trees per acre, and you couldn't do it. And it doesn't make sense to you if you close your eyes and think about such a stand. It just doesn't it doesn't resonate. I mean, it's not reality. So, in fact, this is. I mean, there aren't stands. It's ecologically impossible to have ponderosa pine stands that have combinations of mean size and density that put you up here. And in fact, we can speculate on where that boundary line is. Now, I've placed it here somewhat arbitrarily, and we can quibble about the placement of that. For example, you say, well, why did you place it so far below this particular stand? And my response would be, well, based on my superior silvicultural insight, I think that may have been mismeasured. I think that it's too, it's too far above what I think the threshold is. We might also, speculate on, well, why didn't you move it down further? I mean, you could have snuggled that line up closer to this mass, and that those are reasonable. I mean, people debate that, and we'll talk more about the details of the placement of the line later, because it has some silvicultural implications. Here's another data set. Now, this is aspen from Forest Service Region 4, so we're talking about our part of the Central Rockies. Each one of those circles represents an aspen stand, so we've got combinations of mean diameter and trees per acre. Now, notice a couple of things here. One is that I've flipped the axes on you. So before, I had quadratic mean diameter down here and trees per acre on the y-axis, and now we flipped it, and it doesn't matter. So again, we can flip them back and forth. In talking about size-density relationships, it really doesn't matter where the y-axis is and where the x-axis is. Again, we could quibble about the boundary line, but this is certainly reasonable. You wouldn't put it up here, you wouldn't put it down here. So if we debated the exact placement of that line, it's going to be within some fairly narrow limits, is where the discussion would take place. Okay, so now something about that boundary line. First of all, now this is the school answer. The slope of the boundary line is constant. So the slope of that line, and remember, if we did this in a curvilinear form, if we plotted these data not with a log-log transformation, but with arithmetic axes, this wouldn't be a straight line. This boundary line would be curved. But the slope of the linearized version of that boundary line is a constant. So the idea here is that the boundary line for ponderosa pine, the boundary line for aspen, the boundary line for sugar maple, etc., is the same. So there's a single slope for the boundary line for each species. Now, for each individual species, whether it be lodgepole pine or sugar maple or ponderosa pine, each species has its own intercept or level. So there's a unique boundary line for each species. So if we were to plot the boundary lines for every tree species in the world and superimpose them, we'd see this swarm of parallel straight lines if we plotted them in a log-log format, and they would be parallel but at different levels. All right, and then secondly, for the intercept of the boundary line, or its level, for a given species, let's say sugar maple, that boundary line is independent of site quality. So the idea here is that you've got one boundary line for the species. It doesn't matter if it's sugar maple growing on a really good site or a relatively poor site, you're going to have a single boundary line. Now, little truth in, or for the sake of transparency here, we can push that. We can push that to that assumption to the breaking point. But the kind of the idea that I like to use here is that if the site isn't so poor that you're not even going to think about managing your species on that site, absent that kind of extremely poor site, this generality holds. All right, we have some data here, and each one of these represents a lodgepole pine stand, and there are 3 different symbols there, but that's all lodgepole pine. And these data were collected in northern Utah and on the Medicine Bow, south central Wyoming, just north of the Colorado border. Lots of stands. I've forgotten how many of them there are there. There's a bunch. They range in age, and more to the point, I mean, the point here is that there's tremendous range in site quality, and as quantified with or indicated with site index. So what we did, I think the high, base age 100, the high is about 95 feet. The low is something on the order of 40 feet or maybe even a little less. So a huge range in site quality as indicated by site index. And what we did here before we displayed these data in this figure is that we just did a sort, a rank order from the highest site index to the lowest, and then broke the data set into 3. So there's the upper third, middle third, lower third with regard to site index, and then assigned a symbol to each of the 3 classes and plotted it. Now the challenge here is which is which. Is it the triangle that represents the highest site and the circle the lowest site, or vice versa, whatever? And the point is you can't tell. I mean, there's no statistically, we've looked at it statistically, there's no significant difference. And so this is supposed to illustrate for you the generality that the size-density relationship is independent of site quality. Now, that doesn't mean that site quality isn't important. It is, but will not in terms of size-density relationships. So there's the boundary line, and we would use this boundary line whether we were working with lodgepole pine on a good site or a poor site. Now, there is another way to think about size-density relationships. So what we're going to do here, we have a boundary line for some hypothetical species that we're interested in. So there's that species boundary line, and we're going to look at what would happen if we had a young stand, has this initial density, and those trees, we're going to watch them grow. Now there is no time on this figure, but as we move the cursor along this trajectory, that really indicates stand development. So the stand is, individual tree growth is increasing. Stand moves from stage A to stage B, eventually it gets to stage C, and then finally self-thinning starts. We're in stage D. The idea here is that the population is going to get somewhere in the neighborhood of that boundary line, and then self-thinning is going to maintain the size-density relationship somewhere on or just below that boundary line. Okay, and I've drawn this here so that you can see how I've drawn it, and not right on top of the boundary line. Now, what if we had a stand where the initial density was substantially higher? You're going to see the same basic thing. It would move like that. Much lower density, it would take, the trees would be much larger before they started to self-thin, but you'd see the same sort of trajectory. Now, what about the influence of site quality? We know that that's important. Let's imagine two stands, same initial density, and one of them is on a good site and one of them's on a poor site. And the idea here is that the poor site stand is going to move along this trajectory slowly. Individual tree growth is, with or without competition, is going to be relatively slow. In contrast, on the good site, same trajectory, but much quicker. Okay, much quicker. Now, that brings us to the end of part 2, and we will continue next time with in lecture 3.